Welcome back, PlayBASIC coders. Let's check out the little library. Have a quick talk about what it is. What the library is doing is gives us a representation of a frame buffer that can be user defined. So in this case, it's I think it's 128 by 256, and then we can set the pixel size as well. So the actual window is 512 by 512, and the pixel size I think is set to 4 by 2. So each dot is a little rectangle pretty much. I've got a bunch of primitives I can draw onto this frame buffer. It's from lines, rectangles. There's a sprite there too, but you can't really tell. It's where the mouse pointer is. It's this thing, this little brackets thing, that's actually a sprite. The green things are a rectangle. Got a line being drawn, some circles, of course, just for basic primitives. We've also got a font capability there too. It's got to be loaded in and palette mapped and then imported into the library, and then you can just use the internal text command to draw text. Exit it. That's a resolution. Go down to, quite low actually. I think it's 8 by 8 to make it full screen at that resolution. So most functions have clipping. The background is being imported as a picture, which is a capture from Mario, and then just copied to the background buffer. So we treat that buffer like it's video memory in a classic 8-bit system or 16-bit system. Okay, so what do we actually have? We've got a sprite concept. We've got a limited number of sprites purposely. Each sprite has a limited size, but they can use the entire palette of the 8-bit. So there's a byte per pixel internally, and this thing here, this loads the sprite. Let's take a look at it. It's just loading some data statements here where I've defined as these binary things here. That's our triangle shape with our... Now, these are 2-bit, and the sprite can actually handle 8-bit. We can test that just, for giggles. Just go index equals random 255. So in other words, any bit that's set will be output as just a random bit, so I can see it. Now you can see clearly where the sprite is in the scene. You have up to 256 sprites. The font's being loaded much the same way as a predefined picture of these 8x8 characters we're running through, and we just assume anything that's not mask color is a particular color index. The background was a bit of a chore. We're loading in RGB mapped images, and we actually need palette mapped images because old systems use palette mapping then. So that every dot on the screen is not actually the color, it's an index to a color table of where should we get the color from. So in this case, we have 256 possibilities for each color, each pixel, and sprites, fonts, the whole screen can only be that. At the moment, it's pretty simple. It's a lot more simple than dealing with like an old system, for example. Set square. Each, a bigger resolution will run slower, of course. Because we are just using dot plots pretty much in the background. The scrolling is actually tied to the timer, so we're still running about 160 frames per second. Yeah. Which is plenty for making a little game, and having that same experience what you would get from programming on retro systems in general. The one thing that's missing actually is an ability to have raster interrupt. You might have noticed in old systems that as the display is being drawn to the monitor vertically, you often have these rainbow effects that are on, whether it's the background color or a color inside the palette. We can do the same thing. just have a little split icon and then get it to modify a color index every scan line, and that would allow you to have a rainbow in the background, much the same way as what you would do it with raster programming on a 64 or an Amiga or those kind of things. So you can actually get more than the 256 colors that are possible on the screen. In this background here, I think it has like 17 colors, 16 colors. So you got lots of free available space there for sprites, etc. So we could do that. It's not that complicated, really. The library is very simple, and so you really sort of understand how these legacy systems kind of work, even though we do have like a pretend artificial system. Like, I think systems like the Neo Geo and have very high sprite counts, but they have very small sprites. So here you've got 256 sprites that are available to you. That's the limit. You could just bump the limit in the source code. It wouldn't really make any difference. The sprites here have a predefined size. That's the maximum they can be. They can be smaller than that, but that's the maximum each sprite buffer can be. And they're drawn not on any priority. They're drawn on their order in the array. So sprite 1's drawn first, 2, 3, 4. So if you wanted to have priority in your scene, you would have to manage the sprites and then render out the sprites, select which sprites you want to give the order of rendering that you needed. That's just how you would do it back in the day. The sync is doing the work. It's just running through the pretend frame buffer, and we've got a couple of banks there that represent the memory, the video memory of our pretend system. We're doing a sprite render, so actually sprites are independent of the background. They don't actually impact the frame. So each frame, what we do is we copy the back buffer to a temp state, draw the sprites, draw the scene, and then at the very end we reset the back buffer. So we render the sprites onto the back buffer in our little pretend system, display this out to the monitor for the user to see, and then we clear them off as if they weren't there, which gives you the illusion of how sprites work as in hardware sprites, not blitter-based objects. You can do the same thing here. You can actually just call draw sprite inside your loop, whatever you like. That will paste the sprite onto the back buffer. Then it's part of the image. We've got a maximum of up to 8 pixels by 8 pixels in terms of width that can be outputted. And here, as you can see, it's not doing anything fancy. It's just grabbing the source pixel, packing 4 of them into here, and then writing them out as an integer. That's to do, so 1 pixel in the frame buffer becomes 8 pixels on the actual outputted display wide. And then vertically we're doing the same thing. We're just running through and drawing the same strip multiple times. So if we're doing it once for a 1 by 1 or twice so we can, there's speed on the table, just things like that there. Most of the graphical functions are all the same. Open screen, we're just allocating a buffer for our back buffer, filling it full of a bunch of default information there, so we can have a look at the screen when I was testing it, giving it a default palette of a bunch of random RGB stuff. That will have no impact on it. We're writing over these colors ourselves. We've got a palette function to read and write colors from the internal palette. Got this limited number of colors, so you can access the array. You can write these arrays yourself, but the function interface is there to make it sort of easier. We just got LowRES dot, same principle as what PB's using. So we've got a bit of a clip in front of it. We're poking into the frame buffer this particular index. That probably doesn't need to be there. That's been updated since that was written. Point's the same. You've got a v-strip function to draw a vertical straight line, horizontal straight line, box, which is just the v-strip functions. So even that horizontal strip function there, that could just be fill memory. But it's been left to be, so PB is doing all the work. The only part that really is native is the palette mapping render strip stuff. Wherever that was back in here. That's the palette map library in there. And that was added to PB years ago for its internal image format. So we needed palette mapping to do color reductions of when you were saving images in PB's own format. That's why they're there. So just expose them, give you a bit of an oddity that you can use yourself. It does mean you have to sort of understand how this stuff works. That's the trade-off there, isn't it? If you don't know what palette mapping is, then that's not going to be of much use to you. But anyway, the little library here with loading our font, setting up our screen, looks all very normal. We're creating a sprite and copying some data into the sprite's pixels because the sprite has its own buffer. If you wanted to change the pixels, you have to copy a new frame into the buffer. That's what you would do. We've got our sprite handles there. This is the backdrop, and the inner loop is just grabbing the mouse, rendering that backdrop with our scroll X register is just how much time has passed since we started the application. If we divide it by 20, we could modify it at different rates based on what how much time we want to scroll the screen by. You can do it frame by frame. Who cares really? But I just don't use time in this particular demo. Position sprite should be familiar to PB. Filled circle, familiar to PB. People. Whenever you see index here, we're talking about color index. So that's not the RGB value, it's the index of this color in the palette. I'll just run it again before the ambulance goes past. If I hit enter, I can change the palette. Yeah, all the colors in the background see are very low, the low indexes. If I just randomize that, you probably see what I mean better. Randomized palette, that'll do us. In the randomized palette, we're creating one base color and then we're fading or shading all the other colors. We just want to let's just do random for every color. RGB. And we've set the highest one to be white. So anything that's in that color will be white. But this could as well be, color 8 or something like that. Index 8. And when we hit enter, anything that's index 8 will be white. So we're just randomly changing the colors as we go through. So to fade the screen out, you don't fade the pixels, you fade the palette. The limitation is you've got this very restricted number of colors. You've got to be very careful about how you use them, etc. That's just like programming on old computers. This is just a bit of a side project, a bit of something fun for people to mess around with. Back to 128, have our fatter pixels there. Kind of like the way it looked. Yeah, nice and chunky. Nice and chunky. Enter. So to use this, you're going to have to do the resource management yourself. That's the difference. That's one of the things that people just don't understand today about legacy programming in general. These old computers, they were very fixed and very had rigid designs, and you have to fit your solution into how it likes to work. Anyway, thanks for watching. I'll see you next time. Bye. Thanks for watching, and if you want more programming content, please subscribe to playbasic.com.